Alrighty, so we're back again. This time we're going to be talking about section 2.6, which is all about something, well, that's exciting, that this section called trigonometric limits. And so the main sort of tool that we learn here, we actually get two. We get something called the squeeze theorem, which is what we'll start with. Right, and that says that if you have a lower bound to some function that we're calling f of x, and you also have an upper bound, so you have a function that is always going to be less than or equal to the function you care about, and you have another function that's always going to be greater than or equal to the function you care about, and the limit as x goes to some value of the lower function is equal to the limit as x goes to the same value of the upper function, and that's equal to some number L, then if both of those things are true, then the limit of the function in the middle, the one that we said we cared about, is also L. All right, so we have this sort of, it's called the squeeze theorem, because we have this sort of idea that, let me get some colors in here, our lower function, right, maybe looks like this, but it's coming up towards L here. And then we have our upper function, all right, it's doing some stuff, but it comes down towards L there. And then we have, let's see, a color that's actually going to show up. We have our F, right? So if we have this graph, obviously it's not going to be too hard to tell that the limit of f is L, right? But this is sort of the idea of why we call it the squeeze theorem, is that the upper function and the lower function, since we know that f has to be between them, if they're both going to the same place, then f has to be going to that same place. And sort of we'll do a couple of problems where we can use that in and of itself, but the main reason we have the squeeze theorem here is to get a very particular thing, right? So as a reminder, this is just to supplement our book. I'm not going into all the details here, right? But the book works out the details of why this following thing is true. Right, so if you're interested in the algebra that they do to figure that out, or really the trigonometry that they do to figure that out, you can look it up in the book. But for now, we know this is an inequality that we know, right? So if we want to know I can spell squeeze, probably. So if we want to know the limit as theta goes to 0 of sine theta over theta, which we talked about in one of our previous videos, really last video, that this is something where this looks like it goes to 0 over 0, so it's an indeterminate form if we do substitution. But it's not one that we can figure out algebraically because there's no way to factor and cancel, right? These sine theta and just theta by itself are as simple as they get. there's no way to factor them or simplify them in any way that would let us cancel out something, right? So we can't do it algebraically, so we want to figure out some other way to do it, right? And the squeeze theorem says if we want to know this, then we need L of theta equal to cosine theta, and U of theta equal to 1 to go to the same place. And it turns out that limit as theta goes to 0 of cosine theta, right? First thing we should always try is substitution. And then if we get some sort of indeterminate form or problem, then we can work on it later. But in this case, when we do substitution, we get cosine of 0, which is just 1. And the limit as theta goes to 0 of 1, right? That was our very first rule of limits, is that if there's none of the variable there, so no thetas in this case, we just get it back exactly. So they do go to the same place, right? And so what the squeeze theorem says is that since something less than the function and something greater than the function go to the same place, then this guy goes to that same place. So we know that the limit as theta goes to 0 of sine theta over theta is going to be 1. Right? So the squeeze theorem is one of the things that we have from this section that's going to be in our toolbox from now forward. This is another thing that needs to be in our minds from now forwards, right? This is another tool whenever we want to solve a limit. If we can pull that out somehow, if instead of factoring and canceling, we can pull this out in its entirety, then we can use our other limit laws. And we'll talk a little bit how we do that later. We'll do a bunch of problems practicing that. The other thing that we have, and again, I'm brushing over some details because they're pretty explicitly laid out in the book. We can also get that the limit as theta goes to 0 of 1 minus cosine theta over theta equals 0. Right? So this is another one where if we use substitution, we would get 0 over 0, so we'd get an indeterminate form. And it's one where if we followed it all out, we would actually be able to factor using conjugates. So not quite factor, but we'd be able to simplify using conjugates and trig identities and actually make it look like that. Right? So actually, why don't I go through that real quick? Right? So on the surface, it looks really simple that we have here, but I know my trig identities, so I'm pretty sure that multiplying by the conjugate of what we have up top is going to be handy. Because that means we get up top 1 minus cosine squared theta right? And that looks a lot like, and by looks a lot like, I mean it is one of the Pythagorean identities. Right, so this is why when you're in pre-calculus, you did all that trig stuff, all of those trig identities. Well, it's one of the reasons why. Is so that you could simplify things like this. Right? And now that we have this, we still substitute to get 0 squared over 2 times 0. So we're still bad. But here's where we get to use our new identity, such as it is, right, I can write this as limit as theta goes to 0 of sine theta over theta times sine theta over 1 plus cosine theta. Right, so all I did was factor out things from the top and the bottom. Right, whenever you're multiplying fractions, you just multiply straight across. So you can also unmultiply or factor in the same way. And I know that this guy is going to go to 1 because of what we have up here. Right, and this guy is going to go to 0 divided by 2. So this equals 1 times 0 or 0. Right. So that's one of the ways that this new trigonometric limit can come in handy, is we can pull out factors and get rid of our indeterminate forms in places where we might not have been able to otherwise. Right? So the squeeze theorem is more than just these guys, right? I'm actually gonna circle this because this is another thing that we'll want to keep in mind. Now, whenever we see something like this, we don't have to do all this work again. We've done it once and then we're over with it. We can just use this identity now. But problems having to do with the squeeze theorem, we might get something like, let's see, the limit as x goes to 1 of x minus 1 times sine of 1 over x minus 1. Right, so if we plug in here, right, if we do substitution, right, we get 0 times sine of 1 over 0. And this isn't even one of our indeterminate forms, right? This isn't 0 over 0. It's not infinity over infinity. It's not 0 times infinity. It's not infinity minus infinity. It's just not good, right? It's sine of infinity, which is not one of our indeterminate forms. But one of the things about squeeze theorem is that whenever you see a sign, really it's here that we should be on the lookout for it. Whenever the bad part is within a sine or a cosine, then you've got a ready-made possibility for a squeeze theorem problem, because one of the things that we should remember from trigonometry is that both sine and cosine are always going to be in between -1 and 1. Right? Always, no matter what. It doesn't matter what you plug in there. It doesn't matter what x is. It's always going to be somewhere between -1 and 1. Both sine and cosine can't get out from in between those two things. Now, that's not this entire function. So if I want to get the actual function in the middle here, I have to multiply both sides, or all three sides rather, by x minus 1. Now this is the f of x that I care about, so that means this must be L of x, and this must be u of x. So what I need to check is the limit as x goes to 1 of L of x. Well, that's just a polynomial, so I know it's continuous and I can just substitute in. So that gives me 0. The limit as x goes to 1 of u of x. Again, u of x is just a polynomial, so I know I can do substitution. And these are the same, so the limit as x goes to 1 of x minus 1 sine of 1 over x minus 1 must equal 0. Right, so some things to sort of keep in mind to bring the squeeze theorem into it. It's not the only thing that'll work, but it's certainly a common one, is that if you have a bad part when you substitute in that is completely contained within sine or cosine, then you have an excellent starting off point, right? Because it doesn't matter how bad the stuff in here is, sine or cosine of anything is going to be between -1 and 1, right? And then all that's left is to check and make sure that what you get when you bring the rest of the function in still goes to the same place. All right. So that's, in general, how you use the squeeze theorem. Now let's talk a little about how we're going to use our trigonometric limits. All right, so let's start with a cosine one. So we have the limit as t goes to 0 of 1 minus cosine of 2t all over t. Right, so we can do substitution, and it's always a good idea to start out that way. So if we substitute, we get 1 minus 1 over 0, so we get 0 over 0. Right, so it's an indeterminate form, so there's still some hope, but it's not, but there's nothing we can factor out there. Now, this looks a whole lot like the trigonometric limit that we already have, but our problem is that these two aren't the same thing, right? If we look back up here, the sort of key thing that we have is that these two pieces look exactly the same, and that exactly the same thing is going to 0, right? So our problem is here that the thing inside the cosine and the thing in the denominator are not the same thing, right? They are both going to 0, though, otherwise we wouldn't have this indeterminate form, right? So what we can do is a quick substitution that lets us get that 2 sort of out of the cosine, right? Cosine is not a linear function. We can't just pull the 2 out in general, but we can make a substitution. And let's say that that 2t is equal to x under our substitution, right? So that means that we're looking at 1 minus cosine of x, which is a good start, right? It means that even if we bring in some complications on the denominator, that can be pulled out because that's just a polynomial, right? So we want to get rid of all of our t's, which means we need to figure out that t itself is equal to x divided by 2, or 1/2 times x, as it might be easier to see. So this t down here becomes 1/2 times x, right? And the other t that we have to deal with is this one, right? Now remember, for limits, you always want x, or whatever the variable is, going somewhere, right? So we can't just replace this t with 1/2 x, right? That's not the way our limit notation works. We always want the variable going somewhere, right? So what we really want to do is, what is the limit as t goes to 0 of 2t, right? And that's going to be, whatever that is going to become our new limit here, right? And it turns out we can just do substitution, and that gets 0. So we actually just get that x is going to 0. Right, so this still doesn't look quite like the trigonometric limit we already have, right? But we can factor this 1/2 out, right, and get 1 over 1/2 times 1 minus cosine x all over x, and this piece looks like it exactly, right? So we can use the product rule for limits to say this is 1 over 1/2 times the limit of this guy, which, if we recall from all the way up here, is equal to 0. So it turns out that one behaves pretty nicely. Right? So get another one in here. So here we're going to have the limit as x goes to 1/2 of sine of x minus 1/2 all over 2x minus 1. Right? So again, we have something where when we substitute, we get sine of 0 over 2 times 1/2 minus 1, which is 0 over 0. Right? So that gives us the hope that the trigonometric limit will work out for us. And the main thing that we can't fiddle with algebraically is this stuff inside the trig function, so we're going to do another substitution, right? So maybe we use theta this time. We'll set it equal to x minus 1/2, right? And then we can notice that 2 theta is equal to 2x minus 1, which might come in handy. And we also notice that the limit as x goes to 1/2 of x minus 1/2 is 0. Right? So all of that put together tells us that this transforms into theta going to 0, right? That's what this tells us. And on top we have sine of theta, and on the bottom we have 2 theta. Right? So remember, the things that are important about these trigonometric limits are that the thing that's inside the trig function is the same thing as what's on the denominator, and the limit of the variable, the thing that's inside the trig function, is going to 0. Right? So all we have to do is pull out that 1 over 2. So we get sine theta over theta. And then we can use the product rule to get 1/2 times 1, which means overall we get 1/2. Right? And so that's the basic sort of way to get any of these. If you have something that looks like sine of something over a polynomial, right, and you wind up with 0 over 0, then you can probably massage it to look like sine theta over theta, where theta is going to 0. Right? If you have something where it's 1 minus cosine of a polynomial over another polynomial, and you wind up with a 0 over 0, you probably can massage it using this sort of pattern, doing a substitution where the thing inside the trig function becomes a new variable, and then you just pick out all the rest of it, the denominator, the limit part of it, and substitute entirely for that new variable, and then you'll get something that looks like one of our trig limits, right? And we can even expand this a little bit and do stuff with tangent. So we might have the limit as z goes to 0 of tangent of 5z over tangent of 3z. Right, and if we do substitution again, we get tangent of 0 over tangent of 0, which, if we recall from our trig lessons, that's 0 over 0. Right? So this one can get a little bit tricky because it doesn't, on the surface, have any sines or cosines, and that's the only way that we know how to use these trig limits, right? But if we recall from last section, when we were talking about algebraic tricks, one of the tricks that we always want to turn to when we have non-sine or cosine trig functions is turning them into sines and cosines, right? So we have tangent is sine over cosine. So we have this monstrosity of a of a fraction here, right? And so now we can kind of see that we do have this sign here that we really like having to do one of these trig limits things, but we know that we're going to want, in this case, a 5z, and in this case, a 3z, to be on the denominator of this fraction. But, because I am wise in the ways of multiplying by 1, I can multiply by 5z over 5z here. And I can multiply by 3z over 3z here. Right, because I want what's inside the sine function to be the same as what's on the denominator, and I want whatever that thing is to be going to 0, right? And if z is going to 0, so is 3 times z. So now I'm just going to rearrange everything, right? So I'm going to break this up into 5z times sine of 5z over 5z times 1 over cosine of 5z. Then I'm going to write this as 3z times sine of 3z over 3z times 1 over cosine of 3z. Alright, and so if we just glance over it really quickly, this is our trig limit that we learned in this section, so is this one. This guy is going to be fine because cosine at 0 is just 1, so he's not going to give us any problems. The thing that would still give us problem is the z, but we can cancel that out. Right? So once we cancel those out, like in last section, it's time for us to try subbing in again. Right? Or using our product rule, rather. Right? The 5 and the 3 stay what they are. The sine of 5z over 5z goes to 1. 1 over cosine of 5z goes to 1 over 1. Sine of 3z over 3z goes to 1. And 1 over cosine of 3z goes to 1 over 1. Right? So we wind up with 5/3 as our limit there. Right? And that was using a combination of the product and quotient rules, which, since all of those guys had limits and none of them were equal to 0, was a fine thing to do. Right? So this was using the product and quotient rules for limits. Right? And that's about as complicated as these guys get, right? It's always going to be about making sure the thing inside the trig function is equal to the thing that's on the denominator. If you're dealing with a cosine, you're going to need 1 minus that cosine. Sine can just be by itself. And whatever this guy is needs to be going to 0. Right? Maybe not directly by what it says here, but it needs to say that it's going to 0. Right? So next time we're going to talk about what happens when x is going to infinity. And we're almost at the point where we're going to wrap up this talk about limits explicitly and get into some derivative stuff. So I'll see y'all next time.